Okay, so here's where we were. So now we're going to talk about a seemingly completely different topic, and that is determinants. So I think some of y'all have seen the formula for determinant before. So this is the formula for a 2x2 determinant. Anyway, if you haven't seen it before, it's pretty easy to remember. This first term here, AD, is just that times that. And then the second term, BC, is that times that. So it's, green minus blue, right? It's an easy little pattern that you notice. A little notational alternative is to write it with kind of absolute values. I've used this sometimes. You'll see that I used it here. But there is an awkwardness to using this notation because it looks like absolute values. And importantly, determinants do not have to be positive, right? So anyway, for your consideration. Next thing is, notice this formula is just for 2x2. So what's the formula for a 3x3 determinant? It is weird. There it is. And the pattern, so you don't just memorize, character for character. The pattern here is, we go across the top row, and you'll notice that those top row, elements are there. Right? For each entry in the top row, let's look at just the last one arbitrarily. For each entry in that top row, you cross out the row that it's in, you cross out the column that it's in, and you look at the 4 elements that remain, right? And then you write down the little 2x2 submatrix, they call it, and take the determinant of that. So it's a really weird little formula. 3 separate terms. For each one, you get the corresponding entry in the top row times the determinant of the corresponding submatrix. It's weird. And then there's one other element to this formula that I glossed over that we do need to talk about, and that is this little minus sign. That minus sign has to be there. If you don't put this minus sign in here, then the resulting object that you would have is not algebraically interesting, and it doesn't connect to geometry, and it's just no good. So you got to put that minus sign in, only on the second term. Very strange. Now, just in case you're like I would have been thoroughly unsatisfied with that explanation, I claim there is a pattern at work here. And we're not going to go into this because we're not going to go beyond 3x3s in this class. But if you did talk about a 4x4, the pattern is plus minus, plus minus, plus minus, like that. And so this minus is part of a pattern, plus, minus, plus. It's just a pattern that's only negative in a single place. Right? So anyway, take Math 221, Math 216, Math 218 if you want to see more about determinants. Determinants are shockingly interesting, mysterious even. But anyway, we're going to do only a very limited amount of it. But anyway, that's the formula for a 3x3 determinant. And now, why do we need to know determinants? What's interesting about determinants? Some of y'all may have seen in a high school algebra class, like an Algebra 2 class, that if you have a pair of simultaneous equations, the determinants can tell you something about the solutions. Do y'all remember seeing those formulas? Like Kramer's rule, something like that. If you haven't seen it, no big deal. You see it in a linear algebra class. But it turns out, and I didn't know this in high school myself, turns out determinants are very strongly connected to geometry in a way that's really hard to see coming. Very, very surprising. Here's the first one. It takes a while to state this. Suppose you have a pair of vectors A, B in R2. We're going to start off with a two-dimensional version of the theorem. Okay, pair of vectors. There's a couple things you can do with this pair of vectors. One thing you can do is you can make the first vector the first row and the second vector the second row and result, therefore, in a 2x2 matrix. Now, I just made that up. There is no law that says that when you have two vectors that you have to assemble them into a matrix. I'm saying let's do it just because. Okay. The other thing you can do with that pair of vectors, and I can't remember if I have a picture here. I guess I don't. Okay, shame on me. Let me draw a picture. Second thing that you can do with those vectors is you can take the first vector like that and the second vector like that, viewing them geometrically, and make the corresponding parallelogram. All right, so out of these two vectors, I have two vectors in R2. I can make a matrix. I can make an algebraic object, namely a matrix. I can make a geometric object, namely a parallelogram. And the shocking thing is that this geometric object and this algebraic object are closely connected to each other by way of determinant. Very strange, but here's the connection. If the matrix, if this listing of vectors, A first, B second, by the way, notice whichever one is listed first becomes the first row, whichever one is listed second becomes the second row. Right, so the ordering matters. If this listing is in counterclockwise order, then the determinant is positive. Do this in orange. The determinant is positive and equals the area of the parallelogram. And related, sort of the flip side, if the listing is in clockwise order, then the determinant is negative, and the absolute value of that negative determinant is the area. This is weird how this works out. So the geometric sort of orientation of the list relates to this algebraically defined formula for determinant. And in both cases, the determinant tells you the area by way of absolute value. It's like, you gotta be kidding me. I mean, how could this possibly be? I mean, look, how would you compute this area normally? I mean, let's pretend this wasn't Math 212 and you just had a couple of vectors given. Well, you'd probably try to drop a perpendicular here and then think in terms of, using that old formula from geometry, the base times height, once you drop the parallelograms are no big deal. So, but how do you drop that perpendicular? Well, you'd be thinking in terms of, okay, well, let's compute the component in that direction, and oh my gosh, it'd be such a pain, right? Or you might, compute this angle and compute that perpendicular by doing some trig from computing that angle. There's different ways you could go about it. But what this formula is telling you is that you don't have to do all of that complicated geometry work. Just AD minus BC does it. It's phenomenal. It's a very surprising formula. There is a third case, by the way, of course, and that is it's possible that something goes wrong and the vectors are neither clockwise nor counterclockwise. Like, one of the vectors could be the zero vector, or the vectors could be parallel. I mean, something anomalous, right? And if any of those anomalous things happens, then the determinant is zero. So anyway, that's the theorem that handedness. Well, I'll say the order, the geometric nature of the order relates to the sign of the determinant, and in all cases gives you area by way of absolute value. Okay. All right, so, whoa, crazy. And there is a three-dimensional version of this theorem as well. So if you have three vectors, A, B, C, you can make a matrix by making those the rows. Oh, let's see, color choices. Oh, gosh. Okay, well, I'm just going to have to mix my colors. You can make a matrix out of those three vectors. You can also make a parallelogram, parallelepiped, they call it, three-dimensional kind of parallelogram. Out of those three vectors, you make the corresponding sort of, box-like thing. Right? And in a highly analogous way, the determinant of this matrix relates to the geometry of these vectors in this parallelogram. So when the determinant is positive, the listing of the vectors is a right-hand order. When the determinant is negative, that listing of vectors is a left-hand order. And in all cases, the absolute value of the determinant gives you the volume of the parallelepiped. Which is just, again, shocking. I mean, the formula for determinant, okay, it's a little weird, but it's four-function arithmetic. It's really easy to compute a determinant of a 3x3 matrix and then compare, think about how you compute this volume. Oh, it'd be kind of a nightmare because these vectors are pointing every which way, and how do you drop a perpendicular from this vector down to here? It'd be somewhere in the middle of this parallelogram down here. Right? It would be hard. Determinant does it for you. It's a really surprising result. I think this is very cool. I'm not going to prove this theorem in this class. The topics in this section, in order to prove everything from scratch, there's a bunch of different ways to kind of connect all these dots, and they all have ugliness in them somewhere. And I just don't think it's a good use of our time to go through all of the ugliness. What I'm going to do is I'm going to assert this as a fact, and then everything else in this section I'm going to prove using this as kind of a foundation, a very convenient foundation to work with. So anyway, this is just a given. So you need to know that this is true. You need to know how to use this, but we're not going to prove it. Okay. So a quick example. Let's go back to where we can see what's going on. Here we go. Suppose I've got this trio of vectors here. First vector, second vector, and third vector. And I want to take that trio of vectors. I want to form a parallelepiped out of them. What's the volume of that parallelepiped? This would be a killer high school geometry problem. Right? How do you find that volume? Okay, well, no sweat. You take those vectors and you go there and there and there, and you take determinant following this weird little rule, and that determinant is -10. That tells you that the volume is 10. Remember, the volume is the absolute value. Volumes can't be negative. Just like distances. Distances can't be negative. They're intrinsically positive things. The negative is what tells you something different. The negative here tells you that listing is in left-hand order. Everybody good? Okay. All righty. So, with all of this observed, we're now ready to finally actually get around to defining our thing called cross product. By the way, I should recognize something odd. We've already defined a product of two vectors. Didn't we already define multiplication? Right? Well, let me just remind you, when you make up a definition, all you're really responsible for is that your definition connect somehow to something interesting, something geometric, something physical. There's no rule that says there's only going to be one such construction that has some sort of geometrically interesting connection. And it turns out that in R3, there are two of them. It's a little unfamiliar, but there are two perfectly reasonable, perfectly interesting, geometrically natural products. And as a result of which, by the way, it becomes very important to use the terminology. If you just say V times W, that doesn't make any sense anymore. We've got two different multiplications. Do you mean the cross product of V and W, or do you mean the dot product of V and W? Times, you just got to drop that terminology. It's absolutely unacceptable. Ditto, you can't just write VW. This does not, that is completely unacceptable. It is not clear what that means. And sometimes students are like, well, yeah, but from context, you should have known what I meant. And absolutely not. Nobody does that, and it's not something that it's just not clear. So make sure to write, if you mean dot product, put the dot in there, and if you mean cross product, put the cross in there. These are essential. We good? Everybody on board? Okay. All right. So, here you go. Here's the formula. Just like with dot products, I'm going to write down a formula, and I'll persuade you later that this is actually interesting. So, there's the arbitrary formula. It's even weirder than the formula we wrote down for dot product. The formula for dot product was at least kind of organized, kind of simple. This is weird and complicated looking, and it's not at all clear where this is coming from. It mysteriously, though, is going to have some very nice properties. Now, I'm going to start with some at a glance, seemingly boring observations of algebraic rules. At a glance, it's like, oh my gosh, I remember all of it. Isn't this stuff I learned in elementary school? And here, not only are these not what we learned in elementary school because these are different operations, at closer inspection, you notice they aren't even really that analogous. So, most glaring, that minus sign, right? What's going on there? V times W is not the same as W times V when you're doing cross products. That's weird, right? Now, one way to say this is that cross product is not commutative. Okay, and that's true, and that's disappointing. Right? But here's a different way to say it. Cross product is exactly the negative of commutative. That's interesting again. Right? So the fact that it's not commutative is that's kind of a pessimistic point of view on this fact. There is an interesting property in what happens when you switch with the cross product. It's just not the interesting property that we're accustomed to. Okay. All right. This one down here is really weird. It at a glance sort of looks like associativity, and I guess it kind of sort of is in a way, but notice that here we were crossing V and W. Weirdly, this W that was part of the cross product there has jumped out and is not part of the cross product over here. There's a shuffling of the vectors in this second property that's being listed here. So that's weird. And we're going to come back and talk about that in a little while. Third property, and this is vaguely suggestive of an old property of dot products. Remember, if the dot product is 0, the two vectors are perpendicular, well, orthogonal. Right? If the cross product is 0, then they're parallel. Asterisk, or one of the vectors is 0, or they're both 0, something anomalous like that. Okay. So weird. Okay. All right. Moving along. Here's another property. This is a really important property of cross products. One of the most important properties of cross products. The cross product is always orthogonal to both of the individual input vectors. So when you cross V and W, the result will be orthogonal to V. It will be orthogonal to W. Notice I said orthogonal, not necessarily perpendicular. So this is arguably a stronger statement in the sense that this applies even when one of the other of these vectors is 0. And even if the cross product itself is 0. Okay. All right. Now, this I'm going to prove two different ways. The first way I'm going to prove this is by direct calculation. Remember, orthogonal means dot product equals 0. Right? So if I want to show that the cross product is orthogonal to W, let's say, if you want to show the cross product is orthogonal to W, well, take the dot product, show that you get 0. That's what orthogonal means. This is a calculation that you can do. Everybody should do this once in their lives. It's not that bad. There's only 6 terms in the formula for the cross product. The formula for the dot product that results is just a matter, multiply and add. It's pretty straightforward. It'll take you 30 seconds, right? But I think it's a healthy exercise. Everyone should crank out this dot product on their own and confirm that everything cancels, as it turns out, and you get 0. And when a dot product is 0, that means orthogonal. Cool? Everybody should do that calculation.
Okay. And then likewise for V, right? So this dot product here is how you show that the cross product is orthogonal to V. Just compute that dot product, confirm you get 0. Okay. All right. Okay. Now there's a bunch more that we're going to say about cross products, and in order to be able to do this, I have to wade through a little bit of algebra. There's no way to avoid this algebra. This algebra is not that bad, but it is going to be a little bit of a wade, so bear with me. So we're going to start off by making this observation, that the cross product can be written as this linear combination. Now, let's look at these vectors in here. The vectors are E1, E2, and E3. So that means that when I say that the cross product is this linear combination, what I'm really saying is that the coordinates of the cross product are that and that and that. I'm really just saying here that the cross product's coordinates are individually 2 by 2 determinants, and you can kind of see that here in this formula here. That is a 2 by 2 determinant. That is a 2 by 2 determinant, and that is a 2 by 2 determinant. So, just notice that green, that blue, that orange, those coordinates are these little determinants, and that's that first observation. Okay. Do be careful of one thing. Notice that this second coordinate I've written as the negative of this 2 by 2 determinant. Now, crank it out. Observe. It's true. Right? What I've written down is correct. There's a common sort of reflex that students have at this time, which is to say, well, yeah, but how about I had this thing against minus signs, and so how about let's switch these 2 columns, in which case then I can get rid of that minus sign, and now my formula is simpler. Very common reaction to students to have here. And you could do that. That's not wrong. But it is counterproductive. For the following reason, and that is that having written this like this, you'll notice that this formula involving some 2 by 2 determinants is itself the formula for a 3 by 3 determinant. And remember the formula for a 3 by 3 determinant, you go across the top row, and those are the things that get multiplied, and then you look at the sub-matrices, and don't forget your plus, minus, plus. So we need that minus sign in there in order to make this connection to this being a 3 by 3 determinant. Okay. I'm going to take a quick pause and give you all a chance to ask a question here. Is everybody on board? I have a tendency to talk a lot. Yeah, go ahead.
Is there a defined formula for the cross product in R2?
That is a great question. No. The cross product is peculiar to 3 dimensions. There is also not really, there is not a binary cross product in R4 or higher either. It is a peculiarity of R3. Now let me correct my little asterisk there. There is a construction in R4 and higher that has certain properties that behave kind of like what we're calling the cross product here, but it's not really a product, and it's a strange little construction. It's nothing we need to worry about. So yeah, as far as Math 212 is concerned, this is strictly 3 dimensions. Thank you for that question. Anybody else?
Okay, so we're wading through the weeds here for the moment. A little bit of algebraic weeds. First we made this observation here. Now we've made this observation. You'd be right to complain, by the way, that, wait a minute, matrices are supposed to have elements that are numbers. Can you stick a vector in there where a number should be? If I stick a vector in there, can I also put a bicycle in there? What are the rules? Can you just write down anything? Can you just stick anything you want to inside of a matrix? Okay, valid complaint, and technically this is a little bogus. So this is what I'm going to call a symbolic matrix, because I don't want to have to deal with that complaint, basically. So by symbolic matrix, what I mean is, look, if you write this down pretending that it makes sense, and if you pretend, following just the symbolic rules to compute the determinant, as if that makes sense, then it gives you the right formula. Okay. All right. Okay. Next observation. Again, sort of proceeding through the weeds. If you take this cross product and if you dot it with a third vector u, then you get this thing over here. Now, this is not such a hard calculation. I just wish I could get this to all fit on the screen. But here, so let's do it like this. So here are the three coordinates of the cross product, v cross w. We've already observed those are the coordinates, and you can see those coordinates here, here, and here. Right? Whereas, I'll do this in blue. This vector u has coordinates there, there, and there. And I hope this is familiar. Look, the way you do a dot product is you take the two vectors and you multiply their coordinates sort of pairwise and then add, right? So that's all that this observation is here, is that take the existing formula for the cross product and you write down the dot product and you get this. And then you notice that this too is a 3x3 determinant. Like so. Yes?
Is it still considered a dot product even under the minus sign?
Yeah, no, great question. Great question. So that minus sign, remember, is part of this. It is part of this that second coordinate here. So this. Let me be careful how I underline this. This second coordinate is this whole thing, including the minus sign. Does that make sense? Yeah. Right. And again, and you got to just look at the devil's in the details here, but V1W3 minus V3W1, but don't forget the minus sign. This is actually V3W1 minus V1W3, which is exactly what this is. Yeah, right. Yeah, great question. So neat result then. Very surprising result. But this weirdo little construction, a dot product of a cross product, is computed by a determinant. And the pattern is lovely. Notice that in this, by the way, they call this a triple product because it's a product that involves three vectors, u, v, and w. In this construction, the first vector of the triple product, make that the top row. The second vector of your triple product, make that the second row. The third vector of your triple product, make that the third row. And triple product is determinant. Okay, everybody on board? It's just algebraic weeds. Why this is useful to us is going to reveal itself momentarily. Right now it's just weeds. Okay. All right. So let me try to give you an instinct for where the value of this equation is going to come from. It's going to come from the fact that this, and again, common story in math. If you want to learn about something, find a way to relate it to things that you already understand. Right. And I claim that's what we've actually got here. There are sort of three operations in here. There's dot product, which I already understand. We understand a lot about dot products. They involve, cosines and projections, and we have good understanding of dot product. We have a good understanding of determinant because it's connected to volumes and order, handedness order, and things like that. Right? So we have a good geometric understanding of determinant. We have a good geometric understanding of dot product. And from that, we're going to be able to cleverly infer some neat geometric properties of the cross product. Okay. So this thing here that we understand, that we want to understand, that's going to come from what we already understand in this formula. Okay. Alrighty, so here's the first little example that I have of this in action. Let's look back at remember we needed to compute, for example, that dot product as part of a previous, I asserted that this cross product, I claimed that it's orthogonal to the first vector v, and the way that I've suggested for y'all to do this, everybody should crank this out once in their lives, is if you want to show two things are orthogonal, write down the dot product, show that it's 0. Okay, and what I advised at that time was crank it. Just, write out all the terms and just get it all ugliness on the page and then start canceling. It's not that bad. So what I'm going to show you now is a way to kind of clever your way out of that effort, which I think is nice. And that is as follows. Now notice how effortless this is going to be. This dot product that I need to compute to show orthogonality, that dot product, as it turns out, is, notice, a triple product. And triple products are determinants. Now, there it is. Okay, fine. Determinant. What do I know about determinants? Determinants tell me volumes, right? So, first vector, v. Second vector, wait a minute, also v. And then third vector, w. Right? This determinant, absolute value, of course. But that determinant can be computed by understanding this volume, this being the volume of a parallelepiped that you get when you take those three vectors and you make the little parallelepiped ring. Well, the big coincidence to notice is that the first two vectors are the same. The first vector is v, second vector also v. Those two vectors are the same because what I'm explicitly interested in is showing that a cross product is orthogonal to each of the individual vectors. That's why I'm looking at one of these individual vectors. That's why I have two v's here. Right? So no coincidence here. The orthogonality, which relates to a triple product, which relates to a determinant, which relates to a volume. I just have to figure out what the volume of this thing is. And I don't know if y'all have ever recycled cardboard boxes, but that's what this looks like to me. Right? We've got a box that's been smushed down because two of the edge vectors are the same. Right? I mean, this hand gesture that I'm doing here makes a box that's got volume to it, but if two of the vectors are the same vector, it makes a flat box. No volume. The volume is 0, the determinant is 0, therefore the triple product is 0, therefore this dot product is 0, and when a dot product is 0, the vectors are orthogonal. Everybody see what happened there? So, I didn't get my hand dirty. That's what's cool about this calculation. Just using ideas, the connections between our algebraic tools and the geometry that we already understand about them, we've been able to draw a conclusion. And I didn't have to crank anything out. So, I think that's kind of cool. Okay. Okie dokie. Here's the next one. This one's a morally kind of, strategically kind of similar, and that is, let me not get ahead of myself. So, new fact. Given a couple of vectors v and w, I'm going to define the parallelogram. The parallelogram that's defined by those two vectors. I'm going to use this notation. By the way, I made this notation up. Hoping it catches on. But two parallel lines, right? Two parallel lines followed by a list of two vectors, and the implication is that these two parallel lines are, parallel. So parallel, the parallel thing defined by these two vectors. This means the parallelogram defined by these two vectors. So the area of that parallelogram is the length, the magnitude, that is, of the cross product of those two vectors. Weird. All right, does everybody see what I'm asserting here? It's not obvious, not even close to obvious why this is true, but this is what I'm claiming. By the way, before we get into proving why this is true, notice that this is another really strong, I think very persuasive part of the case that cross product is geometrically natural. Cross product, this wacky formula that I wrote down, the resulting magnitude gives you an area. Now there's no contest. Area is an intrinsically geometric thing. So cross product is related directly to an intrinsically geometric thing, hands down geometrically natural. Total eyebrow raiser, right? So that's where we're going with this. Now let's actually prove it. This is what I like to call a mathematical bank shot. I don't know if any of y'all ever played pool. So just in case you haven't played pool, this is just for sort of terminology reasons. But if this is your pool table and there's a pocket right there, right? So a bank shot is where the ball that you're interested in sinking, instead of going straight for the pocket, what you do is you bounce it off of the rail and then have it go into the pocket. And so the reason I call this proof that I'm about to show you, a mathematical bank shot, is because we're going to get to where we want to go by starting off going in a seemingly completely different direction. It's going to seem like we're heading off into a useless area, and then magically, oh my God, we're done. It's just going to work out. Okay, so things that I'm interested in: the cross product, the area of a parallelogram, and the mathematical bank shot is to start off by considering this triple product. Which again, that's not this, and it's also not this, and so why am I thinking about it? Okay, so bear with me. This is going to play out very nicely. This is another one of those situations where I'm going to compute the same thing two different ways. And not because I'm interested in it, because I'm interested rather in that the two results will equal each other. So, first calculation. This is a determinant, which is a triple product. Now let's be real careful about this. This determinant is a triple product of the first vector, second vector, third vector. Right? So determinants are triple products. That's all I'm doing in this first step here. Right? Everybody good? Determinants are triple products. All right. Now next, notice that this is a dot product of a vector with itself, and dot product of a vector with itself is a magnitude squared. And this is not what we're interested in. Right? We're interested in the magnitude by itself, not the square. Okay. All right, there's our first calculation. Now, next calculation, this is a determinant. And another thing I know about determinants, forget triple products, determinants are volumes. In particular, this is the volume that you get when you look at the parallelepiped defined by that vector, and that vector. Let's draw that. Here it is. That vector, and that vector. Ready? Good? Okay, what can I say about this volume? I need to compute this volume. This is just some kind of random parallelepiped, but not quite. These are not 3 random vectors. That's a special vector. This cross product, I already know, is not only is it perpendicular to W, but it's also perpendicular to V. This is not just a random parallelepiped, this is a right parallelepiped, at least right in the sense of it being perpendicular. The green vector is perpendicular to this yellow face. There. And when you have a shape like this where there's a right angle, the volume is that length times that area. Okay? Old high school geometry fact. Volume is height times base. Okay. So, green magnitude times yellow area. And, yeah, so green magnitude times yellow area. Okay. All right. Now notice again, there's this thing that I've computed. I've computed it 2 different ways. I still don't care about this thing. This is the bank shot. I don't care about it. I care about the fact that the 2 results that I've gotten have to equal to each other. So I care about the fact that that is equal to that. Cancel a factor of the magnitude of the cross product, and we got what we want. Right? Cancel one of those with this, and you get the magnitude of the cross product is the area as desired. Isn't that cool? It's a neat calculation. I encourage you to look at other textbooks for a proof of this result. Most of the other textbooks that I've seen anyway prove this result by doing a lot of trig. And there is something direct, and I guess there's an appeal to that in a sense, but there's just so much weeds in just blurting out all the trig that goes into computing this thing and observing that it just happens to work out that, yeah, sure enough, this works. I find it very unsatisfying, the proofs of that sort that involve a lot of trig. I think it's very appealing that we've proved this simply by using established geometric features of our new constructions, right? So there's a lot of ideas that go into how we prove this, but there's not a lot of sort of details, if you will. This is just it takes a certain amount of writing to write down the ideas, but this argument is mostly ideas. So that's why I like it this way. Okay. All right. Lastly, and I see we're short on time. So here's a couple of vectors, V and W, and with this pair of vectors V and W. Now I know a couple of things about the cross product. I know the cross product is perpendicular to both of these vectors. That means the cross product has got a point. Well, it's got to either point that way or that way, one or the other. You give me 2 vectors in space, right? There's only one direction, there's only one line that's actually perpendicular to both of those 2 vectors. Okay. Now here's another thing I know about the cross product. I know that if I were to take these 2 vectors, I just got through proving that if you look at the area of that parallelogram, that area tells you the magnitude of our cross product. And that means that our cross product got to be either, once you know what that magnitude is, either exactly that vector or exactly that vector. right? So the directions of V and W tell you which way the cross product points. The area defined by V and W tells you the length that the cross product points in one of those directions. But there's this remaining sort of like, but there's two different ways. Does the cross product point to the left, or does the cross product point to the right? Which way does it go? Everybody understand the question? Yeah. Mm-hmm.
Can you explain what they and how you know they point in that direction?
Well, I don't know which of these it
So
is.
that it follows along.
Yeah, so one of the first rules that we wrote down for the cross product is that it's perpendicular to both of the given vectors. Right. So does that make sense?
Yeah.
Yeah, cool. So we've got in some sense V and W point in different directions. They define a plane, and perpendicular to that plane there's really only what I'm going to loosely call one direction. Two different versions of the same direction. Okay, so question that remains then is, how do I decide which one of these resulting possibilities is actually the cross product? And the answer comes from right-hand order. As you might sort of, intuition, you might sort of see that that's the only way we can sort of get our hands on this. No pun intended. And the details of the algebra we already have done. It's right here. If we look at this equation right there, notice that this is a perfect square and therefore is not negative. How about that? This is clearly non-negative. That means that this listing here, there's a possibility that one of these vectors is the zero vector, or V and W are parallel. The cross product is therefore zero. But none of that is interesting, because if the cross product is the zero vector, I don't need to know which direction it's pointing. It's the zero vector. Right? So that's not a concern. As far as we're concerned, this is positive. That means that's a right-hand order listing, and that resolves the dispute. Which way does V cross W point? It points in the direction that makes, come on, I needed to get the pencil mode. There we go. That makes V cross W, V, W, a right-hand order. And now I'm going to make a geometric appeal. If 1, 2, 3 is a right-hand order, then 3, 1, 2 is a right-hand order. Everybody see what I'm talking about there? This is just a literally hand-wavy argument, but I think this is very persuasive. So if I cycle through this listing, it remains a right-hand order. And so I'm going to rewrite this fact as V, W, V cross W is a right-hand order. And so said differently then, if you want to know which way the cross product points, take your first vector V, take your second vector W. Your thumb will point in the direction of the cross product. Okay. And so on this picture that we have here, this is not a perfect picture. Drawing these pictures in 3 space is always kind of hard. The way I'm seeing this picture is that V is kind of leaning back into the page, if you will. W is kind of leaning toward us. And with that being the case, index finger in the direction of V. Rotate your hand as necessary. W, middle finger bent in the direction of W. Notice that your thumb points that way. Right. And so this one is the cross product, because that's what makes the listing a right-hand order. Okay, so it's time to quit. Let me just have 2 seconds. I want to start by very quickly, I just want to say that this formula we wrote down for the cross product, again, I pulled it out. Circled the wrong formula. This formula that we wrote down for the cross product, we pulled it out of thin air. It's algebraically arbitrary, so it seems it's just algebra. And notice that what we now have is a completely geometric characterization of the cross product. Here it is. The cross product is the unique vector that's perpendicular to both of the inputs. Length is the area of the parallelogram, and that satisfies the right-hand rule. This is a purely geometric characterization of cross product. Again, that's what makes cross product interesting, is that it is unavoidably geometric. See you later, guys. See y'all tomorrow.